Is my slides is visible? Please confirm.
Yes, sir. Slides are visible.
Great, great. So I was talking about what is the need of pruning, right? So here we have seen like once we will have, okay, once we'll have this kind of image, let's say any image, and we have these kernels where we have value C1, C2, C3, C4. Once we do the convolution, we'll multiply and add. And if your C4 value is the maximum, then the impact of C4 will be maximum. So mean if you have some value which is belonging to this area, maybe not very impactful in the final decision. Or you can say even if you remove them, then also your performance will not degrade a lot. Definitely, maybe possible it will degrade lightly, but not a lot, right? So in that case, this gives a hope. Can we reduce them and can we regain those accuracy what we dropped due to deletion of those parameters, right? So this give a motivation to us. Why? Because there are a lot of redundant parameters. Then can be do not need to include them, and we have some negligible values, means very tiny value that is close to zero. So that can also be removed from the network, and they are not impacting a lot in terms of accuracy, right? So there are variety of pruning. One is the fine pruning, then there is a coarse pruning, static pruning, and dynamic pruning, right? So fine pruning is more on pruning the individual weights, right? So in that case, your network will become very sparse when we talk about the fine pruning. Coarse pruning, when you prune the either a neuron or the entire layer, or you can say a particular kernel, that is the coarse pruning. That will not make your system sparse, but it will reduce the system itself, right? Similarly, we have static pruning that will help us to prune the model after training happen. Like once training is done, then you start the pruning process as a post training operation. Then you have a dynamic pruning as well. So during the training itself, we can figure out which particular nodes are not useful, which particular kernels are not useful. Then we reduce them down. So these are various variety of pruning. So let's understand first weight pruning, right? So in case of weight pruning, you can see in the first diagram, there are like fully connected network. Now suppose I reduced this weight, right? Then what happened? Whatever the connection related to this weight, they are also deleted from the network, right? On the top of it, you can say that you can check out these networks initially have all fully connected, means all network nodes are connected with the next layer nodes. Now it is connected only one layer or two nodes, like which is highest value, or you can which have more than threshold value, right? Then we will keep those connections. The bigger challenge with this method is they are making matrix very sparse. So means once we have a sparse matrix, we required a dedicated, you can say mechanism, dedicated hardware that can deal with the sparse matrix. Otherwise, we are not getting any benefit of this sparseness. So if you want to get some benefit of this sparseness, we require dedicated hardware. Now the question is how to select which part of them. So what they are doing simply, suppose you have values W1, sorry, W3, W4, they have it, and they decided a threshold value. Let's say TH, right? So whichever weight WI is greater than threshold, that will remain in the network, and whichever is less than, they will delete it to make it the sparse. Now, when you say delete, actually it is not deleting. They make that Wi equal to 0. So in short, if you write in the code form, so it will say if your Wi is less than threshold, then Wi will become 0. Else Wi will remain same. Right? Or you can say we are not touching this part that is not required, but just this part is good enough. If wi is less than threshold, then make it 0. Once you make it 0, then it will become a sparse matrix because multiple values will become 0, right? So this is weight pruning. Now you can say how much we have to remove and how much we have to remove from individual layer, or in which layer I have to remove more, in which layer I have to remove less. So in order to give answer of this, we can use the sensitivity of layer. Which particular layer is sensitive to the pruning and how much it is sensitive. So in case of getting sensitivity, what we are doing, let's look into this graph first. We have, let's say we have three fully connected layers, FC1, FC2 and FC3. We start reducing the parameters based on the threshold. Right. So let's say when your threshold value is 0.5, with that we are able to reduce 25% of the parameter. In that case, you can see the accuracy loss, we are not getting anything. No loss means even if you remove 25% straightforward, there is no change in the accuracy. Accuracy will remain 95, or if it was previously 95, it is remain 95. Then we have removed even 50% of the parameter from fully connected layer and other layers as well, like fully connected 1, 2, 3. Then also there is no reduction in the accuracy. Now, once you go beyond 80%, right? Let's say this is your 80%. Once you remove more than 80%, then accuracy drop drastically. So you can say, let's stop somewhere here. So let's say I am removing 75% of the parameters from the fully connected layer and the accuracy drop is just like 0.001%. So that's really nice. Means you already rid of 75% parameter of fully connected layer, which has the highest weighted layer in the entire network. So means you are able to reduce your network by 65% close to, without losing any accuracy or losing only 0.001% accuracy. Now, similarly, you will do the sensitivity analysis to the convolution layer as well. Suppose you have convolution layer 1, 2, 3, 4, 5. You can easily check out initial convolution layer is very sensitive towards the accuracy. You cannot remove a lot from the initial layers. Why? Because they are looking forward for the basic information, or you can say some very primary informations from the you can say from the input image. So we cannot remove those information that is anyways required into the to the network to perform the operation. But if you say further layers, we have like again this has you can say this has a convolution 1 has the highest sensitivity, then lesser than that the second, then lesser than that the third, then lesser than the fourth, then fifth. So you can say as you move forward, the sensitivity also reducing down, right? So you can say you cannot remove a lot from the first layer. So you can say let's remove from con 1, you just remove 10%. Con 2, you just remove 25%. Con 3, you remove 45%, let's say. Con 4, you just remove 60%, right? Similarly, if you say con 5, we are removing the, let's say 65%. So now once you remove all those parameters and you check the accuracy drop, maybe you are dropping 2% of accuracy. So means once you have removed close to 75% of the parameter from the model and your accuracy drop is only 2%. So you will say, yes, it's really beneficial because once you drop 75% of the parameter, what exactly it means? It means you have to do 75% lesser calculation to get the output. You require 75% lesser memory to get the output, and that will speed up your process as well. So that is the beauty behind the pruning. This pruning will help you to reduce down the you can say computation, but that is not reducing a lot into the memory. Now The very first method that was published in 2015, that was the magnitude based method. As I told you, like here we have a threshold, and that compare with the magnitude of your you can say convolution kernel and fully connected layer node value, and fully connected weight value, right? So you can check out, we are not reducing a lot from the convolution layer, but we are reducing a lot from the fully connected layer. So you can say only part that is left is this blue, and this part we have removed. So this is the pruning parameters, and this is the remaining parameter. So you can check out in the LXNet, we are reducing a lot, still we are getting much better accuracy. That is the magnitude based method, right? So what is the problem in this weight pruning that we need to understand? So first thing, the matrix will become sparse matrix, right? As we say, like it required a dedicated hardware if you want to take advantage of that, right? Otherwise, what will happen? They will treat as zeros, and then still you have to require this much space to store. That doesn't make any use of that. So if you have dedicated hardware, then definitely that will be very useful, right? So RAM will be occupied same. Multiplication may be faster because whenever value is zero, then you do not need to multiply. You can easily say its a value is zero. So that definitely improve, but memory requirement will remain same. So you can say space complexity will remain same. Then there is another technique. Instead of weight pruning, there is a neuron pruning, right? So what neuron pruning is saying? So out of these all neurons, you decide which neuron is not that contributing neuron, which is not contributing a lot to the network, and then remove that particular neuron. So suppose this is represented by red here. So we are taking this red, so we selected this one neuron and delete this. Once you say I'm deleting this, whatever connections related to this neuron, they all also deleted from the network. So automatically, this will not make a sparse network. This will reduce the row and column size of the weight matrix. They will not make your weights sparse. They will reduce down the size of your matrix, right? And once your size is reduced down, automatically this will be faster, right? So you do not need any dedicated hardware. Suppose initially your matrix size is 10 cross 10, and once you remove, let's say, one neuron, so it will become 9 cross 9. So automatically this will be faster. So that is neuron pruning. Similarly, we have channel pruning as well, where we are reducing the convolution channels as well. The entire kernels we can delete, right? Which is not useful. Now you can say how to decide. So we said this red one, but how to say which one is red or which one we have to select? There should be some mechanism that can help us to select that particular neuron, that which is not useful. In order to select it, we are using the regularization. And I hope you have already seen this regularization in your previous session somewhere. So what this regularization is doing, they are trying to reduce down the weight size, the weight values. So what regularizer are doing, if you are able to recall, we are adding an additional term, let's say this regularizer term, into the cost function. So suppose you are taking an error, right? Plus this regularizer we are adding into the cost function, or you can say loss function. Now what this regularizer is doing, as our weight value once your weight value is increasing, your error is dropping. Your error will reducing. But this will impose high testing error. And this particular things is known as one thing we have lesser training, or one thing is overtraining. Overtraining means if you are able to recall, that is overfitting. So maybe you are able to recall overfitting. And in order to reduce this overfitting, we are using the regularizer. So what exactly regularizer is doing here? While we are dealing with the overfitting, we are adding this regularizer term into the loss function. So we are reducing the error by increasing the weight. So let me write it here. Error and weight. And regularizer and weight. Right. So you can check out this, if this will become part of your loss function, when this value will increase, whenever your weight value will increase, right? So if this weight value will increase, then your total loss function will increase. So means ultimately what your system will try to do, it will try to reduce down the value. So you can say when error increase, your weight value will decrease. When regularizer will increase, your weight value will also increase. So ultimately what we are doing, we try to reduce the, so what we want reduce the error. So in order to reduce the error, what we are doing, we are increasing the weight. But same weights, if they increase, your regularizer will also increase. So I want to reduce this sum, the total sum. So one part of this, so you can say error is trying to increase the weight, but regularizer is trying to decrease the weight. So means somewhere it will settle down. So ultimately the goal is to understand what regularizer is doing. It is trying to reduce the weight value. Right? It is trying to reduce the weight value. Now once you apply regularizer very heavily, so then the weight value will reduce down further. Now once it is reduced down, what we'll do, we will check from the previous layer and we will force all those connections value 0, which is smaller than a threshold. Similarly, we'll check the output connection and we'll make all those zeros which is lesser than threshold. What exactly mean if you check here? So for example, we are checking individual nodes. So we are checking value of this, this, all. Whichever is smaller than threshold will make it 0. For example, all these will become 0 while we are looking into the Li side. And this also becomes 0. So now once you find out a node where all inputs and outputs are 0, it means they have no impact. So then you will remove them, right? Same thing we are doing here. So add regularizer in the loss function to train and remove all the connections which is less than threshold. And if you have a node which do not have any connection, then just discard them, right? So once you do that, what happens into the weight matrix? So suppose you have removed one layer or one particular node. So then what happened? Whatever the input weight with respect to that node, that will also delete, and the weight with respect to output of that node, that will also delete. So means your layer size, or you can say matrix size for that particular layer, that will reduce down. And once your matrix size will reduce down, then it will become your efficient network, because now your size is reduced down, so you can process this much faster speed. So here it is just one example. Maybe similar 10 nodes are removed, so means your size will reduce further. So that is just one example. So now I'm taking a pause, and if you have any questions, quick questions. So you can drop into the chat box in the WhatsApp as well.
Hello, sir.
Yes, yes.
Sir, what is the difference between dropout and pruning?
Great, great. So dropout is not a permanent deletion. Dropout, what dropout is doing, they are selecting the nodes and they are saying do not modify the weights in that particular iteration. They are not deleting it. But in case of pruning, they permanently delete from the network. So let me take this example here. For example, in this layer, let me do the clear so that okay. So here, suppose I'm saying in the dropout, I selected this and this while we are doing the performance, right? So in the forward propagation, all the nodes will be there. They will contribute their nodes and you will get some error, right? Now in this error, based on this error, you are doing the back propagation. Back propagation means you will update the weights. Right. Now, while you do the back propagation, these two network or these two node weights, like this weight, this weight, this weight, this weight, and this side as well, they will not modify. No change happen in the weights related to these two nodes. But it doesn't mean they will delete it. Maybe in the next iteration, this node is selected for the dropout. So means dropout is temporary, you can say it's selection of the nodes where we do not want to modify their weights value in the back propagation. That is the dropout. But in case of pruning, we are not dropping, we are deleting. Completely deletion means this node will not exist in the forward propagation or backward propagation. Any case that will delete completely. That is the pruning. I hope it answered. Yeah, any other quick question? I hope it answers to your.
Yeah, thank you, sir. Thank you.
Yeah, yeah. Anyone else? Any other quick question?
Sir, in ResNet, uh, to eliminate the dropouts, we give the links. So how do I decide whether uh, that means it is really difficult for me to find out actually whether the dropouts are working or uh, we need to prune particular thing.
No, ma'am. Both things cannot work together. So
Yeah.
while we are
So
training, one,
for me, dropout happens automatically, while as
yes,
pruning is done through us.
yes,
So
definitely.
we find out a node which is not working. So it
You
is
can say
actually
not
dropped out.
contributing.
It is not contributing. That means the weights are there, zero for that particular node.
Right. So
Okay.
then you, yeah.
So I need to keep watch on that particular output of the neuron, whether it is becoming zero. Now to not make that zero in ResNet, we give feedback input from the previous layer, add, so that dropouts will never happen, will never take place, isn't it?
No, like while we are training, the dropout concept is to train the entire network equally, you can say, to reduce the overfit. So what happened whenever a particular node or particular kernel have a dropout, then their kernel weights or their node weights will not be modified. Right. Now, in case of pruning, what we are saying, so suppose we are talking about the channel pruning or node pruning, right? In that case, suppose we decided a threshold, whatever channels that have less than the threshold rate values, or you can say their summation are lesser, then we delete them. Delete means your restructure will modify. Your network itself will modify completely.
Uh, okay. Uh, so once I remove one single node, the learning process is to be done right from the beginning.
Yes, after the pruning, it's a suggestion you have to retrain the network.
Okay.
So that whatever
So now I
remaining.
have a confusion. Now I have confusion because what happens if I start depending on my initial conditions, my
Mhm,
network gives me different output.
mhm.
So for me there is a risk, isn't it?
Output actually, I think output means the if you say output, I'm not talking about the individual layer output here. I'm
No,
talking
I am not
about.
saying that. I am saying overall accuracy only.
Yes,
So,
so that will may be possible, that will reduce slightly, but it will not reduce a lot. So while retraining,
okay,
you can re-achieve that.
okay, okay, okay. Thank you.
Yeah. So it is suggested, like while we are doing a lot of pruning, then it's always suggested you have to retrain once, so that it can regain the network, you can say the accuracy. But while you are doing the regaining, you are not adding any nodes over there. You are not adding any kernels over there. So means size is already reduced. So let me give you example. Suppose I have a network which has uh, three layers, three convolution layer, let's say, and two fully connected layer. Right. And now in this fully connected layer, suppose we have first layer have 100 nodes and second layer have 50 nodes. Right. In this convolution layer, suppose in the first layer we have you can say 50 kernels, second layer have 60 kernels, and third layer have, let's say, 70 kernels. Now we perform the pruning, right? We have pruned this entire network, and now after the pruning we found we have remained with, like, this has 45 kernels, this has 50 kernels, this has 35 kernels, this has only, like, you can say 25 nodes, and this has only 35 nodes. Definitely I'm not talking about the last layer. Last layer we cannot modify, otherwise your output will modify. Before last layer, this is the, so this is your new network, let's say, right? So after getting this new network, what we'll do, we will retrain this small network, which is generated, or you can say which is extracted from this bigger network. So now you will retrain, and maybe your accuracy of this bigger network, let's say 95%, and it is possible you are able to achieve 94.5% after the retraining of this smaller network. So means ultimately your entire network is reduced down. Got it?
Okay, sir. Thank you.
I hope it ends. It
Yes, yes.
great,
Understood.
great. So this is one method, that is the quantization method. Sorry, pruning method. Then there is another method, that is the quantization.
Sir, one more doubt, sir.
Yeah, yeah, please.
Sir, how to select the thresholding in pruning, sir?
Yes, so this is one big research question as well, how to select the threshold, right? So in order to select the threshold, what normally, like, there are two, three methods. One method, first is the, like, you just sum the magnitudes. So for example, you have some the like, for example, you have a kernel, it has 9 values, so you perform the summation, you can say, and this summation is your absolute sum, right? Absolute sum means we are not worried about the negative. Negative will also add as a positive. So you have taken an absolute sum of all the kernels, right? Now next, what we are saying, after that, suppose you got all absolute sums, then you can take average number, or you can say average plus 10, something something. So that is up to us. Or you can say average plus alpha. Now you decide this alpha value, and that will become your threshold. So whichever is more than that, that will remain in the network, and whichever is less than that, that can be deleted from there. Then it will act as a threshold for you. Got it?
Yes.
Or there is another method. Another method, suppose we have taken absolute sum and we sort them. Right? After the sorting, which have higher absolute sum, that will be the first, and which have lower absolute sum, so you can say high to low. Now, suppose I'm saying I want 50% of pruning. So automatically this 50% we have selected and this 50% we have deleted. That is another way to find out that threshold. I hope it answers.
Okay, sir.
Great. So now let's look into the another method, that is the quantization method. So what we are doing in the quantization, if you are able to recall, so let me take you first to understand some basic concept. So suppose I have a waveform, and this has, you can say, analog waveform, right? Now in this analog waveform, suppose I have selected a region. Let me select it, this region. Now I can say how many points I have in this region. So those have a power of unmuting, they can unmute and just tell me how many points in this region.
So can you repeat the question?
I'm saying I have an analog wave, like it can be any analog wave, and I have selected this region of this analog wave. Now I just want number of points in this region.
Infinite.
Infinite point, correct?
Infinite.
Now suppose I want to store this particular wave. So how many values you have to store?
Quantization.
So then what we do? We do the quantization.
Quantization and then sampling.
Right, quantization and the sampling. So what we are doing, with some time interval, we are doing the quantization. And then we are storing few values. So now instead of storing all the values, we are storing these points. That can be a good representation of your waveform. And the same concept we are utilizing while we are dealing with our this big network. We are doing the quantization over there. So let's understand what it is saying. I am saying binary quantization, simple binary quantization. So I said whichever have the positive values which are greater than 0, that will become 1, and whichever weights have the negative values, that will become -1. Means you have only two sets. One set all ones, another set all -1s. Right? So if it is greater than or equal to 0, then it has only 1. And if it is less than or equal to less than 0, then it will become -1. So what happened once we have done this with the entire network? So entire network now remain with either 1 or -1 value. So definitely size will reduce down 32x time. Now the question is how the size can be reduced by 32x? Guess? Anyone? Any guess how size can be reduced by 32x? Anyone? Any guess? Okay, let me give you an idea. Suppose I have a number x, and this number initially it is stored a float value, and that has 32-bit. You can say the memory requirement is the 32-bit, right? Now I converted this x into a binary number that has either 0 or 1. Then it required only 1 bit to store. So I hope you got the idea why it is reduced by 32x. Initially, all the weights are stored in 32-bit float values. to make sure that they have a good precision, or you can say you can say good accuracy. Now what we are doing, the binary quantization, we reduce down all the values in 1 and -1, only two values, 1 and -1, that's it, only two numbers, right? So then your size is reduced down by 32x. Similarly, your speed will up by 7x and accuracy will drop by 20%, top 5 accuracy. But definitely it's a drop a lot, but this gives an idea to the researchers. We can work on this direction and we can achieve much better accuracy. So then what they have done? So instead of saying binary, now they are saying 8-bit uniform quantization. Right? So it means instead of saying this 1 and -1, now you have 8-bit representation. So then this 32-bit information converted into the 8-bit. So that you will have 8-bit to represent the individual information. With that, what happened? Your storage will drop by 4x. Runtime multiplication is much faster because now you are not doing multiplication by 32-bit values, you are multiplying by 8-bit values. And accuracy is dropped, but your you can say model is still acceptable in non-critical task. Let's say you are making some fun game or something, then this will be really helpful for you. Now they said why we are doing this non-uniform. Sorry, why we are doing this uniform quantization. Let's make it non-uniform quantization. So what this non-uniform quantization is saying, the weight sharing, what it is saying, it will say if most of the weights are reside in this region, then the values of, you can say, quantized values will should have more in this region, lesser in the outer region. Still it is 8-bit, but the points, or you can say the quantized, this is the dense quantization, you can say in this region, very dense quantization, and in the outer region, it is a sparse quantization. That will also give you the most appropriate value. Right. So in this case, you are able to reduce the size as well, and you are able to improve the performance as well. Right. So now you can say what are the places where you can do the quantization and how we can share the weights as well. So let's look into this diagram first. Suppose we have these weights, right? So I'm talking about the upper half of this particular diagram. So we have these weights. So what we have done, we have performed the clustering over there. Each have, like you can say 2.09, 1.92, 1.87, 2.12, they are belong to one cluster. So we have given number 3, 3, 3, 3 here. Second, we are saying which are the negative values, they belong to one cluster. So we have given 0, 0, 0, 0. Similarly, we have formed some clusters. Now suppose I formed 4 clusters. So in order to store these values, you required only 2-bit to store this cluster information, in which cluster it is belong. So 2-bit for this, 2-bit for this, 2-bit for this, 2-bit for this, and so on. So first let's calculate how much information we require to store this entire matrix. So it has 4 values, sorry, 16 values. So 16 into 32-bit. So you can calculate later on how much information is required. Now here we require only 2 bits. So 2 into 16 bit for this, and for each cluster we have taken a centroid. So suppose we have 4 clusters, so 4 into 32 bit. Now once you sum, let's say this is your B and this is your A. So this is your A, this is your B. So you will find out A is much greater than B. But while you are looking towards the computation, you can say values, what we are just getting, that is very close to the original value. And that's the beauty behind this weight sharing mechanism. Here we are sharing these weights. So you can say this weight will be shared by cluster 3. This weight will be shared by cluster 2. This weight will be shared by cluster 1. This weight will be shared by cluster 0. And from where this is coming, that is the centroid of that cluster. So with this beautiful concept, we can achieve a high accuracy as well, but it will require very less, you can say, space and high speed as well, right? So this is one architecture proposed by the researcher. They are saying pruning less quantity. So here we are pruning first, then we perform the quantization, and ultimately we are reducing. So 10% size we are reducing with the pruning, and 3.7% size we have with the quantization, and we are achieving almost similar accuracy. I'm not saying same, but similar accuracy. So that is another way to reduce the size of the network. Now, there is one more method, that is the matrix factorization method. And I hope we already aware about these methods. So if you are able to recall, that matrix factorization heavily used in the fully connected layer. Whenever we talk about reduction of the fully connected layer. So what this concept is, that is singular value decomposition concept. And I hope we have seen the singular value decomposition when we talk about PCA, principal component analysis. But there also we are utilizing the singular value decomposition. Right? So what exactly the singular value decomposition is doing? So that we need to understand. Right? So the very first thing, what it is doing, it has a matrix W. That is two-dimensional matrix. Let's say n cross m size. Right? Now what it is doing, it is taking this matrix, okay, here it's a m cross, it should be m cross n, right? Now what this decomposition is doing, it is decomposing this A matrix into three different matrices. So first matrix is U, that is m cross m. Second matrix is S, that is sometimes this S matrix is also known as this. So that is m cross n, and third matrix is R, that is n cross n. So this can be decomposed with three matrices. Now you can say, what is the purpose of this decomposition? Because ultimately size is m cross 1. Instead of storing m cross n, now you are storing three matrices. One is m cross n, second is m cross n, and third is n cross n. So how it is useful for us? Now to understand what we are doing, we are not storing actually the full size of matrix. We are storing only partial matrix. So here you have m cross n, but instead of storing here m cross m, that is, we are storing only m cross k. You can check out here m cross k. Then here we are storing k cross k, and here you are storing k cross n, where k is very less than m comma n, and that is actually storing the values. Now you can say what things we are achieving from this, why we are doing this entire exercise. The beauty behind that, even if you remove them, after that, once you do this multiplication, like between this and this, once you do this multiplication, you will again get a m cross n matrix, and this matrix will be very similar to this matrix. That is the beauty behind this singular value decomposition. How it is doing, the beauty here is this diagonal matrix. The value of these weights are decreasing in the diagonal. That is a diagonal matrix. So you can say the W1 will be highest, W2 will be lower, then again, lower, 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 and so on. Why this is lower? They are saying in order to decomposition, this value are most important. Then this is lesser than the first, this is lesser than the next, and so on. So based on that, you can say I am selecting only this part. Even we are selecting this part, then also while we multiply them and we are getting this value, then you are saying this matrix is very close to this matrix, very similar to this matrix. And that is the beauty behind that. This is the real beauty behind the single value decomposition. Because these top values are the most important values while you are decomposing this. Right? So this will give you the importance of the matrix. So the top values in the K is most important. So suppose I want to reduce by 50%. So what you will do, 50% I will remove from here, 50% I will remove from here, and 50% I will remove from here. Once we want this matrix back, you will do m cross n and you will achieve it. I'm taking a pause quickly, 1 2 minutes, and if you have any doubt, please ask. Anyone, any doubt till this point?
Hello, Vipul sir.
Yes, yes. So I'm waiting for the questions if you have any.
No, sir.
Okay, great. So let's move forward. So we with that we can achieve a particular we can reduce down the matrix size, right? So you can say how much we are reducing, you can check out with this. So suppose your original matrix is n cross n, you're doing the decomposition, you got these three matrices. Now we have selected a k value, and based on that k value we are getting these matrices, right? So you can say once you reduce down, you have much lesser storage requirement. So this particular method is mainly focused on reducing of the fully connected network and whenever you have lesser resource requirement, right? So that is the beauty behind this SVD, right? Now let's see one more variety of architecture, that how we can modify the architecture itself so that we have a lesser requirement of resources. Can we make a new architecture itself, like instead of going ResNet or VGGNet or any other well-known architecture or fully connected architecture, can we modify the architecture itself? So let's understand that. So compression we are doing in the pre-trained model, but architecture is itself like we are using a new model architecture, right? So we need to understand first how convolution is working. Right, so here we have kernel that will multiply with the input values and you got one value. So means ultimately this is your convolution operation, you can say. Now let's look into this convolution operation. Right? Now what input is in this particular convolution operation? It's a 28 cross 28 cross 192. And what output we are getting? It's 28 cross 28 cross 32. Now my question is simply how many calculation or how many multiplication. Calculation means in this time I am talking about the multiplication required to get this output, that we need to understand. So first of all, let's think of, I want this one value, just one single value. For this, getting this one single value, how many calculation we needed to get this one single value? To do that, you have this 5 cross 5 kernel. So let's say 5 cross 5 kernel. and that will go into the entire depth, that will multiply, right? And after the multiplication, they will do all summation and it will generate one value. Means in order to get this one value, what we required, we will be needed 5 cross 5 cross 192 multiplication in order to get this one value. But anyone, any doubt on this? How we need 5 cross 5 cross 192 multiplication to get this one single value? Right? So you will have a kernel, you can say this is your kernel, that will multiply all the values, perform the summation, and then you will get one value. Now, for one value, you require this much calculation. So for 28 cross 32 values, how much calculation you require? So you can say we required 28, 28, and 32 multiplication for this entire block. And that is written here. You can say 28 cross 32 values, and for each value you require 5 cross 5 cross 192 multiplication. So ultimately, if you club them together, you will require 120 million calculation for that, right? Similarly, if you look into the parameters, we have 32 filters, we have 5 cross 5 filters here, and what is the depth of each filter will be 192. So you can compute it here, so you require this much parameter, right? Now let's see, can we reduce down the calculation and the parameters? So what I have done, or you can say what researchers have done, they first use 1 cross 1 convolution. And I want you can say depth of just 16. So now in order to get the one value here, how much calculation we required? So we needed only 1 cross 1 cross 192 multiplication to get this value, because you'll have like 1 cross 1 and that will be multiplied in the entire area and it will add, so you'll get this value. Okay. Now how many values you have? 28 cross 28 cross 16. So we required this much calculation to compute this entire block, right? Now from this block, we want 28 cross 28 cross 32. That is the final output that we are looking for. So in order to get this 28 cross 32, we have used 5 cross 5 convolution. So we have applied a 5 cross 5 convolution here and we got some values, right? So once we got these values, what we are doing, we are doing this multiplication. So how many multiplication again you have to compute? So we required 5 cross 5 cross 16 for this individual value, and for this value we just multiply 28 cross 28 cross 32, and that is written here for first block and for the second block. Once you sum them, it will be 12.4 million calculation. Similarly, if you compute the parameters, you will get 16 cross 192 and 32 cross 5 cross 5, so 16 parameters. Total is this parameter. Now you can check out. Without this modification, we have 120 million calculation and you have 1,53,000 close to parameters. In this case, you have only 12.4 million calculation, that is really smaller, 10 times smaller, and you have only 15,873 parameters. That is also reduced, and you are getting same kind of output. Now you can say maybe it's modifying with the values, right? So by modifying the values, you can say it is empirically proved you are getting almost the same results from there. And that is the beauty behind the firewall, right? So you can reduce down the values of calculations and parameters, but still you are getting the good output. Similarly, there is another, you can say, way to modify the structure, that is global average pooling. So in case of global average pooling, what they are doing, they have, so you can say if you check the LXNet and VGGNet, more than 90% parameters coming from fully connected layer. So this global average pooling actually reduce the fully connected layers parameters. What they are doing, So this is like your fully connected layer. So a traditional VGG 16 or VGG 19 or LXNet. What they're saying, instead of converting into the fully connected layer, they are taking the average of individual layers. So average of this map, feature map. So first output is coming from this feature map, second output is coming from this feature map, third coming from this feature map, and fourth output is coming from this feature map. So here they rid of the completely fully connected layer, no need of fully connected layer. And that itself reducing like more than 90% parameters of the model, right? So that is the beauty behind the new architecture itself. They have imposed a new variety of architecture, right? Then quickly, I'll give like in few minutes the last method, that is the student teacher network. That is very interesting method. What we are doing here, suppose we have these output, single hidden layer output, three hidden layer output, and bigger outputs, like n number of layers is there. So let's understand how exactly it works. So student teacher network, what we are doing, first we are training a bigger network, very big network. Then from that big network, we are training the smaller network. So let's understand this entire concept is known as the knowledge distillation that we are utilizing from our school, our colleges as well. For example, whenever you are going to teach something, then you are giving only 1 hour lecture. But maybe in order to prepare that 1 hour lecture, you have prepared, maybe you have spent 5 hours to prepare that 1 hour lecture. So ultimately, this is you as a teacher, you are giving 10 hours or 5 hours to prepare the lectures, and then you are summarizing it and giving to the in the 1 hour to the student. So it is knowledge distillation that you are doing. So how exactly it works? So suppose first you trained the bigger model with the original data, original label data. Let's say it's a classification model. So you have trained it with the original data. Now what you are doing, once it is trained, we are taking the qubits, right? So let's say these are the qubits value, the last layer. So suppose I have taken these qubits value, right? Or let's say instead of last layer, I will take this as a qubits, this layer. So now the important point, I am keeping this, I'm keeping this as output for our student network. So once you train the teacher network, you are training with the original data, right? That the original label data, or you can say it's a normal training. There is nothing, no difference in a training. You are training with the label data. Now, but what additional we are doing, we are storing. So what we are doing, suppose here we have an input image and we are storing these qubits, right? Now, what is the beauty behind this? Suppose with respect to first image, we have stored a qubit. With respect to second image, we have stored another qubits. With respect to third image, we have another qubits third. Now, qubits means these are some values. Definitely, these are some values. Now, suppose I want to make a network, a smaller network. I'm training only these weights where input value is coming from here and output of this will be these qubits. Just think of that. I have taken a bigger cellular network that is trained here. You have stored these outputs. Ultimately, if you look into, you can say you just crop it here. If this output will match with our smaller network, then definitely you will get the same out. The same thing we are doing here. We store these qubits, and now once you train the cellular network, we are giving the inputs, and the output is this qubits. Once we have trained, then attach this last layer, and you got the original outputs or the outputs that is giving from the speaker network. And this is known as the student teacher network concept. So here you have to do two training. First training for the complex network that will get the gist and generate the qubits for you. Then second training for the student network that is very shallow and that will try to generate the qubits value. Once it starts generating the qubits value, then automatically you are getting the correct output, what is your desired output. And this is your student teacher network. So that's it from my side. If you have any quick question.
Sir, there is a query on the WhatsApp group.
Yes, ma'am.
So she's asking that if we want to use compressed version, how can we initiate that?
Whenever we do some compression, we have to create an independent architect. You can say you have to train at your end for because for different applications, compression can be different, or you can say architecture can be different. So there are few compressed architecture like mobile net is there, efficient yeah, you can say SkuseNet is there, but that is trained on the ImageNet dataset. But if you are looking forward for your own application, then you have to compress the network, then utilize it.
Okay, sir, thank you. Shilpi ma'am, I hope you got your answer. Okay, I think, sir, no more queries are there.
That's good. Okay, if anyone has any queries, you can drop an email to me, or if you have anything to ask later on, you can drop a email to me. That will also work. So thank you for giving me this opportunity to talk about my expertise and my areas of research with the bigger group here. And I hope you got some information from there, and maybe you will utilize it in your research, in your work. So thank you for giving this opportunity to me. Thank you, everyone. Thank you, organizers.
Thank you very much, sir. It's really a great pleasure to have you with us on this faculty development program, and I hope your session will be very benefited for the participants, and they will use all the hands-on experience that they have learned in your session in their research work and in their future work. Thank you very much, sir. It's really a very great session.
Thank you, ma'am. Take care.
So, dear participants, that's all for today's session.